Okay, this is a really important section. This is where we get to talk about Green's theorem. And we're going to use Green's theorem later on when we look at three-dimensional space. Right now, we're just working in two-dimensional space. So this is going to be an alternate way to calculate our circulation and our flux. And the important part with Green's theorem is what we're going to do is we're going to go from a single line integral, which is what we had previously, into a double integral. And once we have gone from a single integral to a double integral, what that's done is it's broken down our circulation and our flux into pieces. Theorem 16.6, this is Green's theorem. This is our circulation form, and then we'll look at the flux form. So we have this curve, it's simple, closed, smooth curve, it has an orientation. It's going to enclose a connected, simply connected region R. So we'll have a curve, we'll have some region R that it encloses, and it's going to be a simply connected region. We're going to have this vector field F. Then recall from previous sections, we have our circulation form, which would be these first two forms. It's a single line integral. Now recall if we take our vector field FG and we dot it with dr, that's the derivative of our curve r, which we could write as a vector with the differentials dx and dy. So once we compute that dot product, we get that middle integral, which is just f dx plus g dy. Okay, so what Green's theorem is going to do is it's going to break it down even further. Over our region, we have this partial derivative of g with respect to x minus the partial derivative of f with respect to y. That integrand is what we call the curl. So let's look at what the curl actually is. Here's some properties below. If you look at this integrand, partial derivative of g with respect to x minus partial derivative of f with respect to y, and I like to write it in the more compact form, what that is it's a rotation within C, and it produces a circulation on our curve C. So we call this the two-dimensional curl, but I'll just call it curl of the vector field. This is the idea here in this diagram. Let's say that you have some liquid. So any fluid, and you have a paddle wheel inside. So that's that little diagram right here. It looks like a little wheel. If it's spinning, so that's the curl, it's spinning, what it's going to do is it's going to produce this circulation, which then produces our circulation on our curve. So remember, the circulation is the net vectors that are tangent to the curve. So if you have a rotation within a curve or curl, this spinning at a point within the curve, then it's going to keep rotating and spinning outward, eventually producing these tangent vectors or the circulation on the curve. So the general idea is that circulation measures the force along the path, the curve. The curl measures the rotation or spin at a point within the curve. And then this f sub y, g sub y, these are just components once we've broken it down into a double integral, where f sub y would be the horizontal component, g sub x is the vertical component of the vector field. So all the vectors in there can be broken down component-wise into f sub y, g sub x. So if our curl happens to be positive, then the rotation is going to go clockwise in the usual direction. If our curl is negative, rotation is clockwise. If the vector field is conservative, going back to our previous section, then the partial of f with respect to y is equal to the partial of g with respect to x from our previous section. So that means our circulation is going to be equal to 0. In this box here, we have the definition of our two-dimensional curl, which again, I'll just call curl. So more formally, given a vector field, partial of g with respect to x minus the partial of f with respect to y is the curl. if the curl is 0, then we say the vector field is irrotational on the region. So what does irrotational mean? Exactly what it sounds like. No rotation, which makes sense. If curl is 0, then there's no circulation, which means there's no rotation. Example 1, we're going to use Green's theorem to compute the circulation. And here we have a disk, R. R is x squared plus y squared less than or equal to 4. So it's this region within this circle of radius 2. But since it's a less than or equal to 4, it's that whole area within that circle, where the rotation vector field is F equal to negative y, comma x. So we're going to compute the circulation by using Green's theorem. And we're also going to verify by using the line integrals from the previous section. So let me first use Green's theorem. Green's theorem says we're going to compute the double integral over the region, g with respect to x minus f with respect to y, dA. I'm just going to go across here. I have my region. I can compute the partial derivative of g with respect to x because this is my vector field. This is f and g, right? So f is negative y, g is x. So the partial derivative of g with respect to x is simply 1 minus the partial derivative of f with respect to y is negative 1. And my integrand becomes 2, which I'm going to factor out. And I'll just have a 1 inside my integrand. So remember, this is a double integral with an integrand of 1. This represents the area of our region R. And that happens to be a circle of radius 2. So if I compute the area of a circle of radius 2, that's going to be 4 pi. Putting all of this together, I didn't even have to figure out my limits of integration. I know that 2 times this double integral over this region, integrand is 1, is going to be 2 times the area of the region, which is 4 pi, and that's equal to 8 pi. Using Green's theorem, the circulation is 8 pi. So although it's not asking for it, I have a positive circulation. That tells me that the circulation is going counterclockwise. Let's verify using our line integral from our previous section. So remember, this is the integral from some a to b. Our vector field dotted with, and I'll write it this way, the derivative of the curve r dt. So in this case, the region is this disk. It's the circle and everything inside it. But if I was to describe the curve would be what encloses the region. So that would just be the circle, not everything inside, which tells me that my curve R is going to be the circle of radius 2. So that can be written parametrically as 2 cosine, 2 sine. Again, I have to state that my t values, since it's a circle, go from 0 to 2 pi. So my line integral has limits of integration 0 to 2 pi. My vector field is negative y comma x. Looking at my curve, the first component represents the x, second component represents the y. So negative y would be negative 2 sine. And then x is just 2 cosine. I'm going to dot it with the derivative of r, which would be negative 2 sine, comma 2 cosine dt. When I compute this dot product, I'm going to have 4 sine squared plus 4 cosine squared, which, if I factor out the 4, would be sine squared cosine squared, which is just 1. This becomes the integral of 4. So that's 4t evaluated from 0 to 2 pi. And verifying with the single line integral, I get the same circulation of 8 pi. In example 2, we're going to use Green's theorem with these two vector fields. And it's going to be over some region R. Notice that I didn't tell you what our region R is. The only thing I know is I'm going to first use Green's theorem with the vector field 0, x. So I'm going to call that 1. And then I'm going to use Green's theorem to compute over the vector field y, 0. I'm going to call that 2. So this first vector field, 0, x. Now remember, I don't know what my region is. So using Green's theorem, it's the double integral over my region, partial of g with respect to x minus partial of f with respect to y. And I know what that is. The partial, remember this is f is 0, g is x. So the partial derivative of g with respect to x is 1, minus the partial derivative of f with respect to 0 is 0. Again, we have the same situation we had before, that this integrand is 1, so this integral is simply the area of my region. Okay, something to note here, going back to our line integrals, is if we have our single integral of f dotted with the derivative of r, that's going to be 0 x dotted with the derivative with respect to x, derivative with respect to y. And because the first component is 0, this just ends up being the integral of x dy. Okay? So we'll just put that aside for now. Let's look at this second vector field, which is a vector field y, 0. Remember, I don't know what my region is. Okay? The first vector field that I used, I didn't have to know what the region is, which is kind of powerful. What this says is it doesn't really matter what the region is. If you have the vector field 0, x, then this integral will always be the area of the region. Now, if we have the vector field y, 0, using Green's theorem, it's going to be the partial of g with respect to x, which is 0, minus the partial of f with respect to y is 1. So this becomes negative 1 in my integrand. I'm going to pull the negative out. So again, it doesn't matter what region I'm looking at. If it's over this particular vector field, then this is going to be equal to the negative of the area of R. And now something to note with our line integrals, and we can look at what we did with our previous vector field 0, x. This actually turns out to be equal to the integral of y dx. So putting all of these together, it doesn't really matter what the region is. This integral of y dx is going to be equal to the negative of the area of R, which means it's going to be equal to the negative of the integral of 1dA. Okay, so combining all of this, I have that the integral of x dy is going to be equal to negative integral of y dx. And both of these represent the area of our region R, no matter what the region is. So why did I go through that? Well, from those two particular examples, we can expand it to talk about the area of any region using our line integrals, and that's what's in this box here. So we could use these line integrals under the conditions of Green's theorem to actually find the area of a region enclosed by the curve. So you can either use the first integral, which is the x dy. You can do negative y dx, or think about adding those two integrals together. Since they are equal, you can add them together, divide by 2, and compute the area of a region using the third form. We're going to try that here in this next example, example 3. We're going to compute the area enclosed by this ellipse. So the first thing I want to do is I want to go ahead and represent this ellipse in terms of a curve R. Now just looking at the form, under the x squared we have an a squared, underneath the y squared we have a b squared, and that's equal to 1. So when I write this curve, I can write it as a cosine t, b sine t. So that would give me the ellipse with a center at the origin, which this is centered at the origin. So my curve is going to be, a is 2, so 2 cosine of t, b is 1, so this would be a sine t. So this would be one way for me to represent an ellipse using the parameter t, and then it's going to go from 0 to 2 pi for my t values, so I get the complete ellipse. Now remember the first component, this is my x would be 2 cosine t, my y is sine of t. I'm going to go ahead and use the first form, which would be the single integral. Now, oftentimes I'll leave off this little circle that means it's a nice closed curve. So if I was going to use the first integral, which is x dy, I'm going to go from 0 to 2 pi, would be my limits of integration. X is 2 cosine of t. The derivative of y, since y is sine, derivative is going to be cosine. And this is dt. And I'll just work across. So 2 cosine squared. So at this point I have a cosine squared. I can maybe use a trig identity to reduce the power of 2, the square. But I'm going to stop. I'm not going to finish computing. I'm going to try that second form, the negative integral of y dx. Maybe that'll give me something easier. So I'm going from 0 to 2 pi. Oops, I forgot my negative in the front. Now y is sine of t. The derivative of x is going to be negative 2 sine t dt. All right, so this gives me a negative integral from 0 to 2 pi of negative 2 sine squared. So 2 sine squared t dt. If I pull out the negative, then this is gone and it becomes a positive. All right, I don't feel like using that one. Why don't I use the third one? So that's 1/2. I'm going from 0 to 2 pi. It's going to be 2 cosine squared t plus 2 sine squared t, right? I'm just adding those together, dt. Right, so when we compare all three of these, in the first two examples, I would probably just use a trig identity to reduce the power on the cosine and the sine. In the third one, although that's the longer integral, it's actually the easiest one for me to compute because if I factor out the 2, I'm left with cosine squared plus sine squared, which is just simply 1. So this would be equal to, if I pull out the 2, the 1/2 and the 2 cancel, and I just have the integral from 0 to 2 pi of 1 dt, which is simply t evaluated from 0 to 2 pi, and I get 2 pi. So although the first two forms were easier to set up, in the long run they would be more difficult to compute. Okay, it was the third longer one that was actually the easiest one to use. Well, now we're going to move on to using Green's theorem to compute flux. So remember, when we talk about flux, all we're doing is computing net amount of vectors normal to our curve. Going back to our previous section, remember we had our flux formula in terms of a dot product. If we were to compute the dot product, we could use this middle integral. So both of these integrals are single line integrals, but now we're going to use Green's theorem to break that up into a double integral. And in this case, the integrand using Green's theorem is what we call divergence. We'll talk about that in just a bit. Okay, so that would be the properties down here. So this integrand, this partial derivative of f with respect to x plus partial derivative of g with respect to y, that's the divergence. Okay, so when we talk about divergence, in this case, we're just looking at two-dimensional spaces. So it's a two-dimensional divergence. It produces the flux. So where curl produced our circulation on the curve, divergence produces flux on our curve. If we look at this diagram below, you can see that inside we have our divergence. We're going to get this outward motion, and it's going to produce the flux or the normal vectors to our curve. Okay. So when you think about divergence, you can think about at a single point within our curve, you have this dispersion or this outward motion. And then similar to curl and circulation, if the divergence is positive, then we say we have outward flux. And we say that that's going to be a source. If the divergence is negative, it's an inward flux. So in our diagram, we have an outward flux. But imagine those vector fields coming inward. So if the divergence is negative, it's an inward flux, and we say that that's a sink, which makes sense. A source means our flux is all going outward. So there's a source and it goes outward, but imagine this as being inward flux. So think about water going down a drain, it's going to sink. So in this box, we have the definition of our two-dimensional divergence. Okay? And if divergence is 0, then we say it's source free, which just means no source, which means no flux. In example 4, we want to evaluate this integral. Our curve C is going to be at the boundary of this disk R. So here our disk R, it looks like the region x squared plus y squared less than or equal to 9. So the region R is an area, it's circular. It's enclosed by a circle of radius 3. Since C is the boundary of this disk, C is the curve, which is the circle x squared plus y squared equal to 9. Now the integral that we're evaluating is given to us here, and we can assume that it's oriented counterclockwise in the normal direction. So this integral looks hideous, and I don't even know where to start. But the first thing I want to notice with this integral is this is a line integral. It's a single line integral. I see that there's a subtraction. I see a dy and I see a dx. So it kind of looks like if I call 2x to the third plus sine y squared, if I call that f, and the 2y to the third plus cosine of x squared, if I call that g, this looks like the single line integral over this curve of f dy minus g dx, which is the line integral for the flux formula. I can use Green's theorem to write this as the double integral over my region, partial of f with respect to x plus the partial of g with respect to y. So let's compute the partial of f with respect to x, since my f is already given there. That's going to be 6x squared. And the partial derivative of g with respect to y is 6y squared. My double integral over my region is 6x squared plus 6y squared dA. I can factor out the 6, and then I would be computing x squared plus y squared dA. And this is one of the powerful things about Green's theorem. Since it allowed me to write my single line integral as a double integral, when I look at this integral, it takes me back to the very first time we talked about double integrals. If we look at this, x squared plus y squared as some r squared, and we look at the dA as r dr d theta, I can simply write this in terms of polar coordinates. I just have to figure out my limits of integration with respect to this region R. And that's going to be a circle with a radius of 3. So my radius is going to go from 0 to 3. And my theta value are going to go from 0 to 2 pi. So I can go all the way back to when we first discussed double integrals. Now this double integral, if I do theta on the outside, is going to be the integral from 0 to 2 pi. And then the radius is going to go from 0 to 3. X squared is simply r squared, r dr d theta, which is why Green's theorem is so powerful. We can go back to the double integrals that we had previously. Okay, so let's just clean this up. This is r to the third dr d theta, which then becomes r to the 4 over 4, going from 0 to 3, and then d theta. That looks like it's going to be 81 over 4. I still have the 6 on the outside. I'll just write this as 6 times 81 over 4, and then this becomes 1d theta, which would just be theta evaluated from 0 to 2 pi. That's just 2 pi. So 6 times 81 over 4 times 2 pi, not a decimal representation, double check me, 243 pi. So this was just sort of a fun example where you didn't have to come up with the curve or the region, and you didn't have to figure all that out. All you had to do was recognize that you were actually given a line integral. So you want to see if you can match it up to either a circulation or a flux form from our single line integrals that we had previously. And if you can, then you can simply use Green's theorem to write a double integral as we did at the very beginning of this course. The next thing I want to talk about is what happens if we have some complicated regions. Well, sometimes you can use Green's theorem, sometimes you can't. It just depends on the region that you're given. In example 5, it says to use Green's theorem to compute the outward flux, so we're going to use the flux formula for the vector field. So we're given this vector field where the first component is going to be f and the second component negative 3x, that's our g. We're given a region. The region is bounded by y equal to 0 and y equal to 4 minus x squared. So let me first do a quick sketch of this region. 4 minus x squared, that's going to be a parabola opening downward. It has a vertex at 4. And it's going to come down and it's going to intersect y equal to 0, which is simply the x-axis. So if you look at this region bounded by the parabola and this line segment, it's not smooth. We're supposed to be using nice smooth curves that don't have like cusps or corners in them. Now let's just say that we can assume the usual counterclockwise direction. But it is a region and it is enclosed by, well, actually you can see it as two curves, right? The upper part, I can call that one curve, and the lower part, the line part, I can call that another curve. So it is an enclosed region. It does have orientation. The problem is it's not a smooth curve. Well, let's see what happens when we try to use Green's theorem, because we do have a vector field. We have our F and we have our G, and we know that we're computing outward flux, so we know we're using the flux formula. If we compute the partial of F with respect to X, that's going to be 0. And if we compute the partial of G with respect to Y, that's also going to be 0. So if we were to set up a double integral using Green's theorem over our region, we have that the integrand is going to be equal to 0. It really doesn't matter that the curves are not smooth. We don't have a nice smooth single curve. Since the integrand is 0, I know that flux is 0 or source free. So you can use Green's theorem when you don't have a smooth curve. It just depends on what happens to that integrand. If it turns out to be some constant number, then we can just go ahead and compute it. And in fact, in some cases, we can even compute it if it's not constant. It kind of just depends what you have. So you can try to use Green's theorem and see if you get something that you can compute. Let's go ahead and do one more example. In example 6, it says compute the circulation and outward flux. So here I'm going to have to do 2 integrations, one for circulation, one for flux. I have my vector field, and it's a simple vector field xy, so f is x, g is y. R is going to be the region of this half annulus. So maybe I'm going to sketch that just to see what it looks like. R is going to go from 6 to 10, and theta is going to go from 0 to pi. And we're going to assume the boundary curve is generated counterclockwise in the usual direction. First thing I want to do is I'm just going to go ahead and sketch this. Again, this is just a rough sketch. R goes, it's a half annulus. It's going from theta 0 to pi. So it's like these 2 half circles. And let's say this is 6 and this is 10. And we're going in the usual direction. So we're going to start out going counterclockwise. And then we have this, do we have to connect these, right? And so if we were to follow this path, this actually turns out to be 1, 2, 3, 4 pieces to this curve. So again, this region that's enclosed, if you look at this region here, it's enclosed by this annulus. It's not enclosed by a smooth curve. But we'll go ahead and try to use Green's theorem like we did before. Let's go ahead and compute our circulation first. So when you compute circulation, remember it's g with respect to x minus f with respect to y over the region. And if we look at our vector field xy, the partial of g with respect to x is 0, minus the partial of f with respect to y is also 0, which simply gives us the integral of 0, and that's 0. We have no circulation. Let's try flux. Remember, when we compute flux, it's a double integral, f with respect to x plus g with respect to y. That would be 1 plus 1, or 2. Okay, so if I factor out the 2, this is the double integral over this region of 1 dA, and I'm computing the area of the region. So geometrically, it's going to be an outer circle minus an inner circle, but it's only half. So geometrically, we can compute this area. So that would just be one way to do this. So remember, we have this 2 on the outside. I don't want to forget about that. So I have a 2. The area of the region is going to be the half of the outer circle minus half inner circle. So 1/2 pi r squared 10 squared minus the half circle with radius of 6. So that's what it would look like geometrically. That's going to be 2 times, let's see. Oh, if I distribute the 2, then the halves cancel. So it's simply 100 pi minus 30, or 64 pi, sorry. Or 36 pi. God, I cannot do math. So the total is going to be 64 pi. And that would be one way to compute the flux. Now the circulation was 0. So there's no spinning, which means there probably is going to be flux. So a 0 circulation with a positive flux makes sense to me. But we didn't have to compute the flux that way. Another way we can compute flux is, remember, we have this 2 in the front. It's going to be the double integral over the region, which we could actually define. Remember, our theta goes from 0 to pi. R goes from 6 to 10. And the integrand is 1, so if I write this polar, it's going to be r dr d theta. And I could see that this is going to be r squared over 2. And in fact, why don't I just cancel the 2 on the outside and the 2 inside the integrand? That's going to be just d theta. Oops. Forgot to go from 6 to 10. That gives me a 6400 minus 3664. So we have the integral from 0 to pi of 64 d theta. And now that's simply 64 theta, 0 to pi. So you see that we have 64 pi. Computing the flux either using Green's theorem or by using the line integral that we had previously. So recall from our previous section when we talked about potential function phi, and if we had a vector field that was conservative, then this potential function would exist, where the vector field would be the gradient vector field of this potential function phi. Well, now that we can compute divergence, if our divergence is equal to 0, that means there's this stream function that's going to exist, and this stream function is called psi, psi. It's going to satisfy the condition that partial derivative of psi with respect to y is the component f of the vector field. Partial derivative of psi with respect to x is negative g component of the vector field. And when you looked at the divergence, partial of f with respect to x plus partial of g with respect to y, we can break it down into pieces where we take the partial with respect to x of psi with respect to y plus partial with respect to y of negative psi with respect to x. If that is 0, because that's the divergence, so that's the condition that needs to be met, then this stream function psi exists. So what does that mean? Well, the existence of this stream function means the vector field has 0 divergence. So the vector field is source free. And we call the level curves of this stream function. So remember, we had level curves from our potential function. So these level curves are called streamlines. In example 7, we're going to verify that this vector field has 0 divergence. So once we do that verification, then that tells me that this stream function will exist. And then we're going to integrate to find our stream function for this vector field. So the process of finding the stream function is similar to the process of finding a potential function. You integrate, then you have this constant that you have to solve for, so you differentiate. Okay, so the first thing I want to do is I want to verify that this vector field 6, 7 has 0 divergence, which just means that when I take the partial partial of f with respect to x plus the partial of g with respect to y, that's equal to 0. Is it? Well, the f is 6, g is 7, so the partial derivative of f with respect to x is 0, plus the partial derivative of g with respect to y is 0, and the divergence is 0. So since divergence is 0, I know that psi exists. So let's go ahead and find psi. Remember that if psi exists, then the partial derivative with respect to x is equal to negative g, which means the partial derivative with respect to x is equal to g is 7, so negative 7. So if I integrate the partial derivative with respect to x, then I get to my stream function psi. If I integrate both sides of this equation, then on the left-hand side I have psi. Now remember, that's a function with respect to x and y. On the right-hand side I have negative 7x plus a constant. But the constant can be in terms of y, so I'm going to write the constant of y, so it could be a function of y. Now the next step would be to find this constant. So let's go ahead and look at psi, take the partial derivative with respect to y, and if I take the partial derivative with respect to y, it's going to be equal to this derivative of this constant with respect to the variable y. Now, if I just look at my vector field and I directly compute the partial derivative of psi with respect to y, remember that's supposed to be equal to the f component of my vector field, so that has to equal to 6. If I compare this derivative of the constant with 6, these have to be equal. And since they have to be equal, what I can do is I can integrate both sides of this equation with respect to y. So again, this is exactly what we did when we went through the process of finding a potential function. Now, anytime that you can see what your stream function is, you can just stop and verify as we did before when we did potential functions. But if I go ahead and integrate both sides with respect this time to y, then I get my constant with respect to y is equal to 6y. Psi is then equal to negative 7x plus 6y. Now let's go ahead and check this just to make sure that we have the correct function. So the property is that if you take the partial derivative with respect to x, it should be equal to the negative g component of our vector field. So the partial derivative with respect to x is negative 7, and that's equal to negative g. So that checks out. The partial derivative with respect to y has to be equal to the f component. Partial derivative with respect to y is 6, which is equal to the f component. So that checks out. All right, so that's it for this section. Well, this would be a nice time to sum up what we did in the last few sections. So recall that if we have circulation, that goes hand in hand with conservative vector fields. To check to see if a vector field is conservative, you compute the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And if that's 0, then the vector field is conservative. But remember, by Green's theorem, that's just curl. So if you do have a conservative vector field, that means you have a potential function phi so that the vector field is equal to the gradient vector field of phi, which means that the partial derivative of phi with respect to x is the f component, partial of phi with respect to y is the g component. And that means that the circulation is 0. If you do have a conservative vector field, remember that when you compute this line integral, f dotted with the dr, that you can use fundamental theorem of calculus, where you take your potential function phi of b minus phi of a. And in this section, we talked about flux and what happens if the vector field is source-free. Well, in that case, divergence is 0, and a stream function psi exists that has the property that the partial with respect to y is the f component, partial with respect to x is negative g. So that means your flux is 0. And going hand in hand with the conservative vector field, regardless of our path or our curve, to compute the line integral for flux, you could simply use the fundamental theorem of calculus and do psi of b minus psi of a. So that's it for this section.